All right, so we've looked at a new way to write a function, g of x equals, say, b plus a to x of f of t dt. And looking at that, to get to an output from x, we're going to start somewhere. We've got this b here that's always going to be there and added. And what does this integral represent? Well, if I've got some sort of rate of change here, then a rate of change times a period of time or of independent variable per independent variable, rate of change per independent variable multiplied is going to give me a change in output from a to x. And I think we can also get that, if that idea is a little fuzzy, going back and looking at the situation from the perspective of this function being a rate of change of a linear function, it might help you see things here a little clearer. So let's take a look at this situation with a linear function. So let's consider that we've got some linear function here, and we'll say that it's just some linear function with a y-intercept somewhere, and I have a point here, a comma b on my function, linear function. If I move to the right a certain amount over here and I'm at x now, suppose I want to get that output value here at x. How could I view that process of getting that output value at x? Well, one way to look at it would be to see, well, that output value is going to be determined by starting at this point here, your point A, B, starting at that y-coordinate B, and then moving up this amount to get to your new point here at x. Well, how could I express that number there, that distance? Well, one way to express it would be it's going to be adding up all of the rates of change of the function from a to x, and the rates of change of that linear function, let's say our linear function is some function in the form of f of x equals mx plus f. My rate of change is m dx. So think about that for a minute. Now, I can use fundamental theorem part 2 to just go ahead and expand that to be y of x equals b plus. Now, I've called this a dx. I probably should call this a dummy variable for my integration. I probably should have called it plus from a to x of m, say, dw or something, so that when I go ahead and integrate, I'm going to get, by fundamental theorem, mw from a to x. So that's then going to equal b plus mx minus ma. We'll go to a new slide. Okay, so we had y of x equals b plus mx minus ma. Factoring out the x there, we get y of x equals b plus mx minus a. Bring your b over to the other side. y of x minus b equals m x minus a. And you'll note there then we have the point slope formula for a line. And again, I think it's kind of interesting, not totally surprising, but it's got to be consistent. But we can certainly look at the fundamental theorem of calculus being quite closely related to our point slope formula that we've studied for a whole bunch of time for many years. So hope that's pretty helpful. And one more thing coming up on the next slide. I'll show you one other way to look at it, and then we'll be done. Okay, so when we had set this up initially, I said we want to get from, say, AB, we want to get ourselves out here an output value for our function, our linear function at x. And the thought was that we would start here at A, at this point, point AB, and to get to that output at x, we certainly are going to move up, or in this case, the way I've set up the line, we're going to move up a certain amount. So you said it was going to be b plus that amount, whatever that amount is up here. Well, another way to look at that amount would be to say, okay, that's going to be, say, delta y. Well, we know for a linear function that delta y over delta x equals our slope m. So then we know delta y equals m delta x. And in this case, we know our delta x is going to be x minus a, and we know our m is what it is m. So that's indeed the distance that, or the number that I'm going to add to b to get to my y-coordinate here at x. So I go ahead and add that m times x minus a. And now the idea is, okay, let's work backwards now from this. Let's say, how can I rewrite this m x minus a? Well, thinking about fundamental theorem of calculus, I can rewrite it as y of x equals b plus integral from a to x of m of some variable, dummy variable, call it dt. Because note, when I take my integral here, I'm going to get an mt, and evaluating mt from x to a, I get mx minus ma. So basically, I've worked backwards here and gone back and set up my y of x, gone from what we know about lines, and then reverse the process and set up the expression, my output for a linear function, in terms of a function defined as an integral expression. So I think we've looked at this pretty thoroughly, and again, I hope it helps.